Something really cool though is to think a little bit deeper about what hyperbolic functions are telling us and what trigonometric functions tell us as well, even with the physical interpretation. Let's have a look at that. Now let's split the world into trigs. So these are trigonometric functions and hypers. And see what they're telling us. To see this from another angle and get a little bit more insight of what these can be used for and what some of the fundamental identities mean, let's look at it geometrically. Now if we think of a point around here given by a coordinate cos alpha, sine alpha, and if we vary alpha along all values, what we get is a circle. And specifically in this case with a radius of 1. Physically what this is describing would be a bound system with negative energy. You can think of this as describing a very specific case of an elliptical orbit, or for example a planet going around a star, or even a star going around a supermassive black hole. In these conditions, you can very easily realize that coordinate x and coordinate y are essentially given by these two terms. And it also makes sense why you can get the fundamental identity, which is, in this case, cos square alpha plus sine square alpha equals 1. Now for hyperbolic functions, let's try to think of a similar argument and point. A point that's described by something like hyperbolic cosine of some variable u and the hyperbolic sine of a variable u. What this describes is not a circle at all, but an hyperbola. It will look something like this. And if you switch the signs, if you write a point here that is something like minus cos h u minus sine h of u, you'll get something similar along these lines. Now these hyperbolas, physically, you can use them to describe unbound systems, systems with positive energy. And you can use hyperbolic functions and this combination to, for example, calculate an hyperbolic trajectory. This is really useful when you want to send, for example, a satellite, a spaceship, out of our own solar system. You want it to not come back. This means you've actually overtaken the binding energy and you've exceeded the escape velocity. Well, these would be useful to calculate, for example, a geostationary orbit, something that's circular, where you'd be moving exactly at the same rate of the Earth's rotation, so that you're always looking down to the same point. And an interesting thing for you to think about is what kind of period you actually need. And if you're thinking 24 hours, that is actually wrong. That is not a geostationary satellite. Now, because of this, it means that you will encounter hyperbolic functions not only when you're solving differential equations, but also when you look at a lot of problems in physics. And perhaps the most impressive and spectacular hyperbolic orbits ever achieved by something, made by humans, are those that are being undertaken by the Voyager probes. Voyager 1 and Voyager 2. They are incredibly far away, more than 100 astronomical units from us, and they're sending data at rates which are incredibly low. If you've been struggling to watch lectures on Panopto, for example, and it keeps buffering and stopping, and your internet looks really slow, imagine if you were trying to receive data from these Voyager probes. The data rate is actually below 1 kb per second. Imagine watching these lectures from more than 150 AU. Then you'd definitely struggle.